All right, hi everyone. Today I'm going to be talking about algorithms and specifically how algorithms connect to everyday problem solving through step-by-step logic. When people hear algorithm, they sometimes picture something abstract or super technical, but algorithms are really just, structured procedures. By the end of this presentation, you should be able to explain what an algorithm is, why efficiency matters, why some problems become hard really quickly. So first, what is an algorithm? An algorithm is simply a step-by-step procedure to solve a problem, and algorithms matter because they help us make important decisions in real systems, like recommender systems, medical diagnoses, and pricing. The reason algorithms are so powerful is that they let us process huge amounts of information quickly and consistently, and that's why algorithms are basically the foundation of modern, let's say, apps, AI, robotics, and a lot of technology we use every day. This slide here is to make the point that you already follow algorithms all the time, even if you don't call them that. For example, following a recipe isn't an algorithm. It's literally a sequence of steps. You do one step, then you do step two, and then if something happens, you do a specific response. Navigating through Google Maps is also algorithmic. The app is constantly computing routes, updating based on traffic, and deciding what it thinks is best for you as the pedestrian. Even sorting your emails is algorithmic, deciding what gets grouped, what gets flagged, and what gets placed at the top. And the face unlock example on the right here is a really good illustration. Every time you unlock your phone with your face, an algorithm decides extremely quickly whether it's really you. What's interesting is that the twist mentioned here is that the algorithm isn't looking at the picture like a human would. It's looking at distances between key landmarks, basically numerical features derived from your face. So this shows a big theme, which is that algorithms often transform real-world things into measurable quantities that makes decisions based off of that. Now let's just talk about efficiency. So efficiency of algorithms can be evaluated by measuring time complexity, which is the time required by an algorithm to run to completion as a function of the size of the input. So what does that mean in plain terms, I guess? And it means that if the input gets bigger, how much slower does the algorithm get? On the graph, the horizontal axis is the input size, labeled n, and the vertical axis is time, labeled t of n. The blue line labeled O of 1 is a constant time, meaning the runtime doesn't really depend on the input size at all. The green line labeled O of n is linear time, which basically means if the input doubles, the time roughly doubles for the algorithm to complete. And the red curve labeled O of n squared is quadratic time. If the input doubles, the work grows about 4 times. The key takeaway is that as the input size grows, these differences become massive, which is something that seems fine at small scale, but becomes unusable at large scale. Now this slide is just here to show a mathematical way to describe how runtime grows, especially in recursive or structured processes. The equation on the slide is this right here, and I'll walk through what each symbol means. So first, T of n represents the running time, which is the time or number of operations as a function of input size n. The squiggly line symbol, means grow like or is approximately proportional to for large n. So it's describing the dominant growth behavior. Next, we have a sum from I is equal to 1 to k. That means we're adding up k different growth components. You can think of each term in the sum as one mode of growth that contributes to the total behavior. Now let's focus on this one singular term here that looks kind of complex. So C of I is a constant coefficient. It scales the contribution of the ith term. N to the power of m minus 1 is a polynomial factor in n. The exponent m minus 1 controls how strong that polynomial growth is. If m is larger, this polynomial piece grows more strongly. Lambda is the exponential factor, and this is the part that can dominate very quickly. So the most important idea is exponential growth dominates polynomial growth as n gets large. So if any lambda has magnitude greater than 1, lambda will explode as n increases. And so practically, this is one reason some algorithms become infeasible. Their runtime has a exponential component to it. And so this formula is basically capturing a mix of polynomial scaling and exponential scaling, summed across components. and it helps explain why some runtimes grow gently while others, blow up. Now we shift into a very concrete area where algorithms really matter, which is searching and sorting. Computers search through data millions of times per second, and whether a method is slow or fast depends on the algorithm. On the left, the slide shows a simple method. I guess imagine scanning through items one by one until you find what you want. That's simple, but it can be slow when the data set is super large, right? On the right shows binary search, when the algorithm cuts the problem in half each step. And so the big idea here is that strategy matters. So if you cut the search space in half repeatedly, which you do in binary search, you get huge speedups. And so today we're going to be using searching and sorting as a familiar example of how algorithm choices power real applications. And so this slide gives examples of where search algorithms show up constantly. Netflix recommends content based on patterns, which involves searching and ranking options efficiently. Google search prunes through billions of pages using rankings and lookups, basically very advanced search and indexing. Spotify fetches songs instantly from huge databases. Again, search and retrieval at scale. And a key point here is that these systems rely on variations of binary search plus smart indexing. The takeaway line at the takeaway line at the bottom really captures it. Your apps aren't magically fast. They're just cleverly optimized, I guess. And so speed is engineered, and algorithms are a big reason modern products feel instant. Now, not every problem is as friendly as searching a sorted list. Some problems grow too quickly as the input size increases. And so the key idea here is that computers can verify answers easily, but finding them is difficult. And these are called MP problems. The intuition is that if I give you a proposed solution, you can check it quickly, but to discover the solution, you may need to explore a gigantic number of possibilities. And so these problems come up in scheduling, routing, cryptography, and game theory. And the reason they become hard is the combinatorial explosion. The number of possibilities grows just extremely fast. This slide introduces an analogy researchers sometimes use to think about MP problem growth. Some compare MP growth to neuronal calcium ion signaling networks and the combinatorial expansion of synaptic pathways. The idea is that as biological networks become more connected, the number of possible pathways can grow explosively, similar to how the number of possible configurations in an MP-complete graph expands. This slide also says that the combinatorial structure of MP-complete graphs resembles neural synchronization patterns in biocognitive systems, and it frames it as graph expansion is like cognitive metabolic pathways. And to be clear, it's an analogy, not a claim that brains literally solve MP-complete problems like computers. But it's useful because it highlights a shared theme, which is that complex networks can create huge search spaces. And so a lot of important algorithms or algorithmic problems are optimization problems. Many problems require choosing the best option, not just any option. Algorithms use strategies to make decisions quickly, especially when the search space is large. And one simple approach is the greedy algorithm. And so greedy algorithms show up in network routing, scheduling, and resource allocation, basically whenever you need a good decision list. And so this slide is about the greedy mindset, maximizing, or this video here is about the greedy mindset, which is about maximizing value within limits. And so a greedy algorithm works like this. At each step, it makes the best immediate choice based on what it knows right now. It doesn't explore every possible combination. It doesn't backtrack. It commits to the locally best option and moves on. And so that's why greedy algorithms are, often fast and practical, but there's usually a big trade-off, which is that the greedy choice is best locally isn't always the best globally. And so greedy methods are powerful when the problem structure guarantees that local improvements lead to a globally good solution, but they can fail when that guarantee isn't true. And so this slide connects optimization ideas to quantum decision processes, at least conceptually. And so the equation shown here is this, and I'll explain again what each part means in hopefully a clear way. And so psi of x represents a state, which you can think of it as a mathematical representation of a system at condition x. And so the summation here means we're combining contributions across different components indexed by I. Alpha at I represents the weight or amplitude of the ith component. Bigger alpha means that the component contributes more strongly to the total state. The term e to the power of I theta is a complex exponential, which you can think of as encoding a phase angle beta. And so when you sum components with different phases, they can combine in ways that either reinforce each other or cancel out. And that's like the constructive and destructive idea mentioned on the slide. And so the slide's point is some theories model decision-making, like superposition, where multiple possibilities coexist mathematically, and the resulting combination shapes what becomes the final outcome. And so the slide also notes that the link to neural microtubule interference patterns is very loose. So you can present that as like a speculative and theoretical, not like a settled fact. And to wrap up today, we looked at algorithms, we looked at what algorithms are and why they matter, and that algorithms help computers search, sort, and make decisions efficiently. Some ideas are intuitive, like binary search or greedy strategies. Other topics become complex quickly, like MP problems and cross-domain analogies. And the big takeaway is that understanding how and why algorithms work builds stronger problem-solving skills, because you start thinking in structured steps and you start paying attention to efficiency as scale increases. Thanks, and I'm happy to take any questions. Bye.